In this paper, we present SmartMocap, a method for jointly estimating human and camera motion using RGB cameras with unknown extrinsic parameters. Existing methods use single or a set of RGB cameras to capture the video of the subject and then estimate his or her motion relative to one of the static cameras. However, to place the estimated motion on the ground plane, this camera should be calibrated with respect to the ground. As we see in this example, if we visualize the reconstructed 3D human motion relative to the origin, the person is placed in the air and his global motion is relative to the camera placed at the origin. In this work, we take a different approach and our insight are following. Our first insight is to set our global coordinate system on the ground plane. Our second insight is to represent the human pose using simple body model, where the human motion is represented as a trajectory of human poses, such that the origin is the ground projection of the simple's root joint in the first frame. Our third insight is to train a variational autoencoder model, which encodes and learns the distribution of human motions in relation with the ground plane. Our fourth insight is to use the 2D human body key points to resolve the human articulated pose and global pose relative to the camera. Given images at t time frames from C cameras, we first initialize the articulated pose of the person and poses of the cameras at each time frame using a state-of-the-art method pair. The person's global pose at every frame is initialized to the mean starting pose in the latent space of our motion prior network. Then we optimize for the poses of the cameras and the global and articulated poses of the person in chunks of 25 frames. Next, we stitch together the sequences such that the person pose at the last frame of a chunk is aligned with the pose of the first frame of the next chunk. We again optimize the full sequence using the same loss function to get the final estimate of the camera and person's poses. Here we show results of our method on a sequence from rich dataset. In this reconstruction, we use 7 static and 1 moving camera. On the left are the views from a static and the moving cameras. On the right is the 3D reconstruction of the person and all the cameras. We can see that our method can accurately reconstruct the motion of the person and the cameras. Here we show the reconstruction of the same sequence by our method using a single static camera. Our method can reconstruct the full motion using only a single camera. This is a reconstruction from a state-of-the-art monocular method, humor. Even though the motion looks smoother than our method, it is inaccurate and physically implausible. The body is floating and full body turns are sudden and unnatural. Here we show the side-by-side comparison using multi-exposure visualization of our result, ground truth, and humor results. We can see that our monocular results are very close to the ground truth, whereas humor results do not even look like the ground truth. It is also an implausible motion where the person rotates suddenly in place. Here we show another instance where our results are close to the ground truth, whereas humor outputs are physically implausible motion. Here we show the results of another method, glamour, along with humor, and compare them with our method on the rich dataset. We can see that the monocular version of our method is much better aligned with the person in the image compared to glamour and humor, and adding more cameras smoothens the results further. Here we show the results of our method on air pose data, which is captured using 2 unmanned aerial vehicles, where one vehicle is hovering in place and the other one is moving. While Aruco-based camera calibration failed on this dataset, our method uses the person itself to calibrate the cameras. To show the ease of use of our method, we collect a new dataset where we record a human playing football using 4 smartphone cameras. 2 of them were kept static, while the other 2 were moving. We show our reconstruction results on this new dataset here. The video streams are shown adjacent to the reconstructed cameras. The 2 moving cameras are in the bottom left and the top right corners. They were moved sideways along the boundary of the field, and we can see that the reconstructed motion is same as seen in the videos. The results become noisy here because the person is not completely visible in one of the moving cameras shown on the top right corner. Our method needs the person to be completely visible in all the frames, else the global position becomes noisy. Thank you.